we know now that stress intensity factor can describe the stresses at the crack tip. So if this is the crack tip, then stresses here can be described as sigma ij equals k divided by root over 2 pi r into f of theta. This k is the stress intensity factor, which is sigma root pi a, and therefore if you happen to plot the stress versus r, if this is r and this is stress, then the stress looks something like this, and this I'm plotting sigma yy, okay, or sigma 2 so, and then I will have to give a coordinate system. So this is x and this is y. So this parameter defines the intensification of the stress, and so it is called a stress intensity factor. And therefore this is a parameter which can describe a value which says that how much this material is intensifying the stress, and therefore it could work as a fracture toughness value if it can provide you something which remains constant for a material. So there are material properties. For instance, density is a material property, elastic modulus is a material property. Then there are several other things which are material property. For example, thermal expansion coefficient is a material property. So resistivity is a material property which is also denoted with rho. This is density, so we can probably write it density. So the question is, what is a material property? Material property is something which is unique to material, and it is described by, it's an inherent property of the material, meaning that the material is resulting in this way. It's behaving in a certain way, and that behavior shows a pattern. Okay, so for instance, we know that some animals will show this kind of behavior. If you throw food, the birds will come and eat it, and so will the dog, and dog will bark and the cat will mew. These are the properties of these animals. They show these kind of patterns, and they do this in a predictable way. So that's the signature, and that's how you know that this is a dog, this is a cat. Also by the look of it, which is also a signature. So those are physical property. Something like the color is also a property. So color of gold is unique to it. It's unique to the material, and when you make it nano gold, then the color changes. It's not golden anymore. It takes a reddish color. So color is also a property. Although two different materials can have same color, similarly two different materials can also have same Young's modulus, but not very close to each other. So steel can be divided into different categories of steel. You can have martensitic steel, you can have Maraging steel, you can have mild steel, and all those things. There is a whole spectrum of steel, and all those, they somehow are in the region of 200 to 230, let's say, gigapascals. So they all have close values. They also belong to the same family of steel, but if you cannot say that mild steel is equal to, or mild steel and Maraging steel are same thing, because one has a yield strength of approximately 200 megapascal and another one has a yield strength of approximately 1000 megapascal. So So these properties can also be very close, but they are the behavior of the material. And similarly, if stress intensity factor has a critical value, so what do you need? How do you know the fracture will happen? Like in Griffith's case, how did we know that fracture stress was a design parameter? That was an important parameter. We knew it because you will be increasing stress on the system, and after certain point, after certain value of stress, the material will not be able to take that load. So we defined stress as a parameter. We also define sigma naught, which is yield strength, as a design parameter, right? So if we can have a critical value of K, so we apply some stress, and then the K reaches a value beyond which material will give up, then that will be a critical value of K, and that we can use as material property. Okay, but material property should not change with size, and should not show much variation with size or change in dimensions. Okay, so resistivity will not show much change because of the change in dimension. Thermal coefficient of expansion will not show any change. Young's modulus will not show any change. Density will not show any change unless you are making through additive manufacturing or powder metallurgy route. So those things we will judge. We will see once we talk about stress intensity factor as material property. But before that, the question is that what is the stress at R is equal to 0? So exactly at the tip, do we know anything there? So the answer is the stress according to this equation will be infinity. So it goes asymptotic as it goes closer. So R is going closer to 0. This is going closer to infinity. So can material experience infinite amount of stress? That is the question. So is that a reality that materials can have infinite amount of stress or not? The answer is no. They cannot have infinite amount of stress.